Hello, grade 11 A-level students. Right now we are going to continue about the organic nitrogen compounds. We have learned so far 27.1 and 27.2. Now we are in 27.3 reactions of amines, the basicity. We know that amines are basic. They react with acid to form salt. This is the symbol of the basicity of an amine. There is a presence of lone pair. This lone pair able to make the diff covalent bond with the hydrogen ion that makes the salt. So alkyl ammonium chlorides, sulfates, nitrates are white crystalline solids. They are soluble in water but insoluble in organic solvents. Why do they soluble in water? Because the presence of hydrogen bonding in NH2. This hydrogen bonding creates polarity in amines molecule. We know that water is polar, so polar can dissolve in polar. Now let's see the next page 452. 453 explains about the amines are soluble in water to form weakly alkaline solutions, just as ammonia does. Ammonia is also weak alkali. This weak alkali due to the partial reaction with the solvent producing hydroxide ion. So the amines react with water, dissolve in water, it will form alkyl NH3 plus, which is a base. Why is it base? Because this one accept proton, while the H2O is an acid because it donates proton. This is acid, this one become conjugate base, and then this one conjugate acid. Table 27.3 lists some amines with values of their dissociation equilibrium constants. The dissociation equilibrium constants for alkaline is called Kb. We know that Ka stands for the acid dissociation constant. Kb stands for the base dissociation constant. There are 4 common organic alkaline. They are phenylalanine, ammonia, ethylamine, and diethylamine. All of them are amine compounds, organic nitrogen compounds. We know here, we already know the formula of Kb because it is similar to the formula of Ka. So in conclusion, the larger Kb, the stronger is the base. Ammonia is included for the comparison. From table 27.3, we can see that electron donating alkyl groups attached to the nitrogen increase the basicity of the amines. So the more of the alkyl groups, the stronger the basic. This is expected since the basicity depends on the availability of the lone pair of electrons on nitrogen atom to form a dative covalent bond with a proton, which is hydrogen ion. Electron donation from alkyl group will encourage those dative bond formation. We can compare here. There are many alkyl around phenylalanine compared to ethylamine and also compared to diethylamine. But phenylalanine, it has lower, smaller Kb values than ammonia, ethylamine, and diethylamine. we are going to discuss the reason. Okay, this one, the availability of the lone pair to make the covalent bond with the proton, which is hydrogen ion. The most dramatic difference in basicity is to be seen in table 27.3 is between phenylamine and alkyl amines. Taking two compounds of the same relative molecular mass and shape, we can see that phenylamine is about 1,000,000 times less basic than cyclohexylamine. Both of them considered to have the same number of carbon atoms, which is attached to the nitrogen. But the difference is the presence of double bond. In phenylamine, the double bond here can rotate. There is a pi bonding system. Similar in here, that makes the phenylamine, it has lower strength of basic compared to these three other organic alkaline. Okay, let's continue. This is because phenylamine, the lone pair of electrons on the nitrogen atom, is delocalized over benzene ring. The bonds around the nitrogen atom can take up a planar arrangement with the nitrogen's lone pair in a p orbital so that extra stability can be gained by overlapping this p orbital with the delocalized pi bonding system of the benzene ring. And then the overlap causing a drift of electron density from nitrogen to the ring has two effects on the reactivity of phenylamine. It causes the lone pair to be much less basic. Less basic means less ability to make dative covalent bond. And then it causes the ring to be more electron rich and so to undergo electrophilic substitution reaction much more readily than benzene because of the presence of nitrogen. So we know from the second property that this phenylamine is much more reactive than benzene structure. The enhanced reactivity of phenylamine in this regard is similar to phenol. We discussed already phenol in chapter 25. An example being the ease with which phenylamine decolorizes bromine water. So phenylamine reacts with bromine water. So the bromine water will decolorize. This reaction similar to the reaction of electrophilic addition of alkene. But in here it is not an addition reaction, but this one is a substitution reaction. But the difference is substitution in benzene ring in here. This bromine does not require any catalyst. We know that if benzene reacts with bromine, it requires aluminum bromide or Friedel-Crafts catalyst. But since the reactivity of the phenylamine is much more reactive than benzene, therefore bromine does not require any catalyst. We shall see a similar drift of electron density from nitrogen when we look at amines in section 27.5. Only the shorter chain amines with 5 or fewer carbon atoms are soluble in water, but the ionic nature of their salts allows all amines to dissolve in dilute aqueous acid. This is very useful way of purifying amines from mixture with non-basic compounds. The amines can be regenerated by adding an excess of aqueous alkali to the solution after the non-basic impurity has been extracted with an organic solvent. Let's see the example of the here. Separation of codeine and paracetamol from a medicine tablet. I'm sure that you have ever heard or ever seen the name codeine and paracetamol in any medicine ingredients. These two are the active ingredient in some medicine that can relieve our disease temporarily from our sickness. So how to separate codeine? So first grind up the tablet with an organic solvent such as dichloromethane. Then shake the solution with dilute acid and allow two layers to settle. Okay, so codeine will form hydrochloride salt and dissolve in hydrochloric acid, while paracetamol dissolve in dichloromethane. We know that from here we know that paracetamol is organic because and also it is non-polar because dichloromethane is non-polar. Codeine form salt. Why codeine form salt? Because it reacts with the acid. So we can predict that codeine contains basic. And then add an excess of aqueous sodium hydroxide to neutralize the excess of the acid and shake with new sample of dichloromethane. Evaporate the solvent to leave pure paracetamol, that is for paracetamol. Okay, so then free codeine will dissolve in dichloromethane. We know that codeine is also organic, similar to paracetamol, but we can separate both of them using their own chemical property. And then last, for codeine, how do we obtain the pure codeine is evaporate the solvent to leave pure codeine. Okay, this one is the schematic of the experiment, how the procedure should be done or should be performed. Okay, and then next I will explain again about the reactions as nucleophiles.